Warm greetings to everyone present here. I, Shritlaya, will be the host for the event. I take this privilege to warmly welcome all the dignitaries, delegates for this virtual lecture on sustainable high-performance concrete, organizing by the Department of Civil Engineering, Anurag University. To welcome is to show honor, to welcome is to establish integrity. I invite Dr. Narendra Garu, Head of the Department Civil Engineering, for a welcome note.
Thank you, madam. So, good evening, renowned speaker, all dignitaries, participants, and my fellow members. On behalf of Civil Engineering Department, Anurag University, I welcome you all to today's IAStructE Joint South lecture on sustainable high-performance concrete from improved construction to long-lasting structures. Organized by Anurag University in association with the Indian Associate of Structural Engineering, New Delhi, and supported by Anurag University and International Institute of Information Technology, Hyderabad. Once again, I welcome invitees, Professor G. Vishnumurthy, Dean School of Engineering, Anurag University, but due to unavoidable circumstances, he is unable to join. Welcome you, sir. And Professor Samin Fatima, Registrar, Anurag University, and Professor Pradeep Kumar, Vice President, South IAStructE, and Professor, Earthquake Engineering Research Center, IIT, Hyderabad. And today's chief guest, Sri Manoj Mittal, President, IAStructE, guest of honor, and guest of honors, Professor Ramchandran, Vice Chancellor, Anurag University, and speaker, Professor K.V.L. Subramaniam, Professor IIT Hyderabad. I welcome you once again, sir. And brief about the registration. Hopefully today, total number of registrants received 207, and 11 members from the other countries, international students, remaining are other different states across India. Like international countries of Philippines, Manali, Muscat, Rambolan, Kadohan, San Andreas, Batangas. So these are a few countries. Participants also joined this event. So it's my privilege to introduce about Anurag University and Civil Engineering Department. Anurag University, run by Gayatri Education and Culture Trust, began offering undergraduate programs since 1918 at the Lalita Degree and PG College. Later, it became known as the CBSR College of Engineering in the year 2002. And then in the year 2012, it transformed to Anurag Group of Institution. After 8 years of excellence, it became Anurag University in the year 2020. And it is located in Hyderabad, Telangana region. Our prime focus to provide the high quality graduate post-graduation doctoral program in engineering, pharmacy, and management field. Anurag offers 13 undergraduates, 13 graduates, 9 doctoral program in the Anurag University. And it is accredited by NBA with all PG programs in engineering as well as pharmacy, and also maintain a consistent NIRF ranking since last 3 years. And this year under engineering category, we have secured 146, and overall ranking falls 152 to 100 back. About the department, it is the youngest department in Anurag University, established in the year of 2009. It offers a BTech, MTech, and PhD program with a different specialization: BTech in civil engineering, BTech in construction technology management, and MTech in construction engineering, MTech construction technology management, and PhD offer all domains, all specializations in civil engineering. Apart from that, after becoming a university, we are also offering BTech honors and minors for the undergraduate students. And also department accredited by NBA in the year of 2018. And with the intake, we have 180 intakes so far, current day, and we have PG intake for 48, and also offering PhD student. We also joined last 1 year. So our department has a committed faculty from various universities like IITs, NITs, universities, and IIITs. And we are also well established with our department, and we have good laboratory and infrastructures. And it also undertake the consultants works as private and government sectors to offer the professional service and society. So we also, as a department, maybe apart from the academic for the student, so we have to engage in the industry oriented courses. We are also updating our knowledge day to day. So we are registered some of the professional society like Institute of Engineers, Indian Society of Engineering Technology, and ICI for the organized students events. So our department primary goal towards sustainable development in all aspects in civil engineering. So I thank all participants who are interestingly chosen this wonderful lecture this evening on sustainable high performance concrete improved construction to long-lasting structures. My special thanks to my mentor and supervisor, Dr. Pradeep Kumar Ramancherla, for his kind support, encouragement to host this event, the joint lecture. Thank you, sir. Thank you very much. Your blessing continue us. I thank you very much, today's speaker, Professor K.V.L. Subramaniam, sir, for accepting our invitation to present joint lecture in the mid of his hectic schedule. Thank you all. Thank you, sir. Thank you, sir.
Thank you, sir. It's an immense pleasure to invite Professor Pradeep Kumar Ramancherla Garu, President of the South, to brief about IAStructE.
Good evening, everyone, and good evening, Shri Manoj Mittalji, President, IAStructE, and good evening, Professor K.V.L. Subramaniam and Narendra, and all the participants. So a very warm welcome to you on behalf of IAStructE. So to tell you briefly about IAStructE, it established in 2002, and mainly it focuses on overall professional needs of structural engineers, or especially practicing engineers. So from time to time, it brings the latest knowledge in the field and disseminates the same to all the fraternity. So it organizes relevant refresher courses, and like IAStructE has come up with a lot of technical documents and like commentaries also. Now coming to today's lecture, and I thank Professor K.V.L. Subramaniam for readily accepting to deliver this lecture on very important aspect, that is sustainable high performance concrete. So this is actually one of the 5 aspects of buildings. We say safety, functionality, sustainability, aesthetics, and economy. Out of these 5, first 3 are non-negotiable items. Maybe you can like negotiate between aesthetics and economy. So safety, functionality, and sustainability. When it comes to sustainability or materials, actually materials come materials are the primary things, and in which what we can think of is concrete and steel. So Professor K.V.L. Subramaniam is championing the concrete as a material, and we are all eager to listen. And now coming back to IAStructE, so on behalf of IAStructE, I welcome all the participants to become members, and also I request Anurag University to start a student chapter. So that's all from my side, and over to you. Back.
Definitely we'll plan for that, sir, in a couple of days. Next.
Thank you very much, sir. I profoundly invite Professor Saida Samina Fatima Garu, Registrar, to address the crew.
A very good evening. One second. Sorry, I'm just traveling, so I'm just connecting up. Thank you very much. A very good evening to all of you. I'm Samin, and I'm very happy that Dr. Narendra has organized this event in collaboration with IAStructE. I also thank the speaker, Professor K.V.L. Subramaniam, Professor of IIT Hyderabad, for kindly accepting to give this talk today on a very interesting topic. And I also thank Shri Manoj Mittal, President IAStructE, and Professor Pradeep Kumar, the Vice President of IAStructE. I think Anurag University is one of the 5 private universities which is set up in Telangana in May 2020. So that was the first time that Telangana has ventured out in setting up private universities, and 5 universities. Actually, we are a brownfield university, which means that we are continuing our earlier institute, and we are converting that into this university. Earlier, we were called as Anurag Group of Institutions, and we had all the engineering programs like civil engineering, mechanical, electrical, electronics, computer science, AI, chemical, all the branches were available. And today at the university level also, we have all the same programs here. But one thing I would like to mention that we have also introduced a PhD program and a couple of new postgraduate courses after we became a university. So there are a lot of facilities which are available now for doing research, and laboratories are being set up and centers of excellence are being set up. I think a 3D printing center of excellence also is there. This talk particularly may be talking about those things, and like Professor Pradeep mentioned, we have to set up a student chapter of IAStructE. A very good suggestion. I think we'll set it up immediately. I'm just waiting to listen to the speaker, because every day we are seeing that buildings are just coming up within no time, and it's amazing. You sleep and you get up and you can see a new building standing in front of your house. So this is the status today of most of the structures that are being built. And I thank once again each and every person who is available here, the speakers, the guests, and my dear students. Thank you very much. God bless you.
Thank you, ma'am.
Thank you very much, ma'am. I warmly welcome our guest of honor, Professor Ramchandran Garu, Vice Chancellor, to address the group.
He will join.
I might join later. It's an honor to invite the chief guest for the evening, Shri Manoj Mittal Garu, President of IAStructE, to address the group.
Thank you, Dr. Narendra and everyone for inviting me to this event. These lecture series is really very interesting and good and very useful to everyone. And as Professor Pradeep Kumar said, that IAStructE is involved with a lot of technical activities, bringing technical documents and all those things. And basically it is a professional body of structural engineers, and almost all major well-known structural engineers are member of this body. And it is a very cohesive and very vibrant body. And we have a lot of linkages with academic institutions. Many professors, eminent professors are involved with our activities in terms of refresher courses, or they are also on our editorial board of our general SED. So we have a lot of linkages with academic institutions, and we have also student chapters in various institutions. So basically idea is to improve the structural engineering education and practice in our country, and we also know there are a lot of issues are there. So we also try to take up the professional issues which are confronting the structural engineering profession with the government at the policy level. So we are involved with all those things. So it is very good that we are having this lecture in association with Anurag University, and we have a very eminent speaker from IIT Hyderabad. So this will generate a very good ecosystem in a learning of various structural engineering issues. So today's lecture is really looks very interesting, because it is regarding sustainable high performance concrete. And so sustainability is again very good, very important, and in my view very we as a structural engineer generally ignore this sustainability aspect in our designing and planning and all those things. But I think this should be our focus, and this should come into the mainstream or main domain of structural engineering. So I was seeing that this lecture is, we will also be talking about durability and 3D printing. I think this will be going to be a very interesting lecture. So I'm very happy that Professor K.V.L. Subramaniam has joined as a speaker today, and I'm very eager to listen to him. Thank you. Thank you so much.
Thank you very much, sir. I take this privilege to introduce the speaker for the evening, Professor K.V.L. Subramaniam Garu. Professor K.V.L. Subramaniam Garu is currently a professor in the Department of Civil Engineering at the Indian Institute of Technology, Hyderabad. He was the Dean, Planning and Development at IIT Hyderabad, and oversaw the construction of the new campus. Before joining IIT Hyderabad, he was a professor and K.V.L. Research Fellow in the Department of Civil Engineering at the Grove School of Engineering, the City College of New York. Dr. Subramaniam Garu obtained BTech in Civil Engineering from IIT Delhi and PhD in Structural Engineering and Materials from Northwestern University, Evanston. After graduation, Dr. Subramaniam Garu worked as a research associate at the NSF Center for Advanced Cement-Based Materials. He was awarded the Early Career Award from the National Science Foundation of the USA for investigating the early age changes in cementitious materials. He received the James Instrument Award from the American Concrete Institute in 1999 for his research on non-destructive evaluation of concrete. He was the chairman, Committee 215 on Fatigue of Concrete of the ACI. In 2009, he was elected a fellow of the American Concrete Institute for notable contribution in the area of fracture and fatigue of concrete. He is an associate editor of the Journal of Materials in Civil Engineering of the American Society of Civil Engineers and is on the editorial board of the Journal of Cement and Concrete Composites. He is a life member of the Indian Concrete Institute and was elected as a fellow of the Indian National Academy of the Engineering in 2021. A hearty welcome, sir. With utmost privilege, I hand over the session to our speaker.
Thank you for the lovely introduction. Thank you first I'd like to thank IAStructE for giving me a chance to present here. So thank you, Mittalji and Professor Pradeep Kumar. And thank you to Anurag University to make this possible. Now that I have the bully pulpit, I can basically go preaching. Once I can share my screen, I'll be on my way. Yeah, so I'm just trying to share my screen. Yeah, so hopefully my screen is loaded once I go into the full screen mode. Yes. So a lot of hype and a lot of build up. Thank you, Mittalji. You really put the pressure on me to deliver, but I'll try my best. But yes, I've purposely hit all the buzzwords that we are hearing lately. Sustainable, high performance. These are things that we all throw around. But there are some fundamental things that we need to address. And structural engineering as a field and then civil engineering as a profession will not advance unless we bring some science into our engineering. We understand the science and particularly the science of the material, then we can use it more effectively. And that is the core essence of sustainability, is to understand the material, use it effectively, and then build structures that long last. That are long lasting. So this is the key or the three fundamental tenets of sustainability. So let me start by first laying my case. And the basic thing is that concrete that we use is basically, very few people know about this, but it is the second most widely used material in the world. It's only after water. The amount of material we produce is about 2 tons per year for every man, woman, and child on this planet. That is the extent, the volume, the amount of this material that we use. And there is no civilization without concrete, at least the current civilization. Now, where do we use it? It goes everywhere, right? From our roads to our infrastructure, bridges, dams, buildings, it's everywhere. So the issue with this, of course, is that concrete is made with cement. And the problem with cement is, if you look at the consumption of cement over the past few years, the past, present, and the future, this graph nicely captures the cement consumption in the past, where we are today, and where we would be going in the future. So if you look at 1990s, starting from there, red is aptly colored for China, blue is India, yellow is all the other developing countries, and the light blue here is the developed, the industrial countries. If you look at it, China, of course, even in 90s was probably the leading producer. But if you look at the cement that is being consumed in China today, it is enormous. And a lot of it goes into infrastructure. They have developed their infrastructure. They have the economy has been growing on the back of the infrastructure that they've been able to provide. If you look at India, we are not far behind. Today, India is the second largest producer of cement, and all of our cement production is captive. We are not in any position to export. Whatever we produce, we consume. But going forward, if we go to 2050, then India would become the second largest, the largest producer of cement and the largest consumer of cement. Now that has a lot of repercussions because of several environmental issues, resource limitation issues, and energy issues that we will have to address. Now, if we are not able to get to this point where we are producing cement in this quantity or find some alternate for it, there is no infrastructure that will come up in place, and then we can forget about having 8.5 or 9 or 10% growth of GDP. GDP cannot grow unless we put infrastructure in place. Now, what are the challenges in cement production? Major challenges in cement production, and of course, the numbers are staggering. In 2050, we need about, the projected demand is 750 million tons of the cement per annum. This is what is the projected demand in India. Now, if you look at cement, the major ingredient of cement is limestone. And today, if we look at limestone, India is a limestone-rich country. So we have not been importing limestone. We use our own limestone to make cement. But the current available reserves of limestone are expected to last 35 to 40 years. Now, this is the good grade limestone that goes into making cement. So that good grade limestone that we would make, would be used to make cement is only going to last us 35 to 40 years. Then, and cement is an energy intensive material. It does take a lot of material, a lot of energy to produce cement. So if you want to continue making cement, we have to not only look for alternates to the primary ingredient limestone, but we also have to look for sources of energy. The third thing that cement has been knocked upon is carbon footprint. Cement has a very large carbon footprint. Today, cement production is the third largest anthropogenic source or anthropogenic contributor of carbon dioxide in the atmosphere. So this is a very heavy price we pay for producing cement. The reason it is the third largest anthropogenic source is not that for every gram of cement, we produce a lot of carbon dioxide, but the sheer volumes. The cement production does involve carbon dioxide production, but the amount, the volume of cement that we produce, the sheer volumes are so staggering that basically we contribute significantly to the global carbon dioxide emission. So these are all major challenges that have to be overcome if we are going to talk about construction of the future, particularly using concrete. Now, how are we addressing this? Some part of this has already started. People started realizing this. We started addressing this. Today, if you look at cement, what used to be cement, it used to be clinker with gypsum. And this is what we call OPC, the ordinary Portland cement. This is how cement was conventionally made. Today, we are starting to look to replace clinker. Clinker is the primary ingredient that we grind to make cement. So we are trying to reduce the clinker factor in cement by introducing additional supplementary cementitious materials like fly ash and slag, most of which are waste materials. So basically, it's a double advantage. We use waste materials, we reduce the clinker factor, thereby we're able to produce concretes which have a lesser of a material consumption and have lesser energy requirement and have lesser carbon footprint. Now, going further now, there are other cements that are in the production where there are alternate cement which is going by the name LC3, where the clinker factor is even reduced even further with the use of calcined clay. And this calcined clay that they use is not a good grade clay. It is basically the waste clay that lies often as mine overfill. And they're able to reduce the clinker factor even more substantially while producing a cement that gives us better properties than even the ordinary Portland cement. So this work, the understanding the chemistry, producing the material, all of this is currently ongoing. Then there's a whole new breed of materials which are called alkali activated materials. They're also called geopolymers, where we basically don't use cement at all. There is no clinker. We directly start with waste materials like fly ash or slag, alkali activate them, and we're able to produce cements, which of course are colloquially, we call them as geopolymers. So these are all concurrent developments that are taking place in the material front, where we are trying to address this challenge that we see in the future of supplying cement that would go into making the concrete that we need for our infrastructure. Now, there are also challenges with construction. And one of the primary challenges with concrete construction is that we rely on forming at site. Forming at site means that we typically assemble the formwork, we pour concrete into the formwork, we wait for some time, concrete takes essentially gains strength, it takes the shape of the formwork into which it is poured, and then we open the shuttering. Now, what that does is that it limits us to using rectilinear shapes. That means most of our structures, if you look around, you can identify rectangular shapes primarily all along. And the reason why we have that is because the formwork limitation. I'm limited by the formwork that I can produce on the site. Now, we know from our basic mechanics that rectangular sections are not the most efficient sections that we can use in construction. Perhaps something like an I or T is more efficient when it comes to a structural shape. But that is limited when we are talking about forming on site. Very few structures will be formed on site where we can do I or T. And even there, it's very limited. The geometry of shapes we can form on site is very limited. What if the optimal shape was not rectangular? What if it was something like this? I could do, I can basically optimize my structural geometry and come up with a shape, but that shape may not be formable on site using the conventional methods of forming. That means I have to step out of this domain, start producing structures more efficiently with less use of materials, which give me the same performance and essentially are lighter and take less material. But then I have to come up with new forms of construction. And this is where the other stream of research is happening in terms of improving construction techniques. Just to the other challenge, and this was mentioned in the introductory messages, is we are all looking to build faster. Everywhere we turn around, we want to have construct a building as fast as we can. Now, one of the limitations here is again the formwork, because the way we make concrete is that I have to assemble the formwork, I have to tie the steel work, then pour concrete. That limits the cycle time that I can do with each slab. So we need to speed up construction. We've managed to do that with improvement in formworks. But what if I can produce concrete without formwork? And that is what we are working on. A lot of us are currently engaged in research and trying to produce this form-free concrete. Form-free would mean that I don't need form. I can directly print a structure. 3D printing is a colloquial term used, but it's essentially adopting the techniques of additive manufacturing into construction. So, which takes us into the domain of digital construction or digital manufacturing. So these are all things that are challenges that need to be addressed if we really need to be, if we are thinking about sustainable construction of the future. So sustainable concrete construction of the future, we have to make concrete responsive to the requirement. That means I have to be able to make concrete that delivers on delivery and placement. I should be able to produce concrete that meets my requirements as I'm placing it. And I'll give you a few examples of what I'm talking about here. It has to be long lasting. It has to ensure performance. It has to basically, once I make a concrete structure, it should perform over its life without having to be repaired, and that life itself should be long. So I'm looking at structures that last long and give me the same level of performance. So if it's a bridge, I should be able to use the bridge. It should be serviceable over the life of the structure. While the life of the structure itself, I'd ideally like to double or triple or make structures that long even millennia instead of centuries. Then we're talking about low quantum material usage. I want to make concretes which use A, produce structures with less use of concrete, B, use concretes with less use of cement, or probably use alternate materials. So these are all the challenges that we are looking at in terms of producing sustainable concrete structures in the future. Now, if you look at this skyline bar chart that has how the super talls have progressed over the years, this is 1930s. The Empire State was the tallest building. As we go across, then of course you come to the Sears Tower here, the World Trade Centers. And as you keep moving to the left, you come to the current tallest, which is the Burj Dubai or Burj Khalifa building. Now, of course, you see that the trend is that we are shooting higher and higher. We are of course, also building faster. While this building took a decade to complete, this current the tallest building was completed in years. So we are already shortening, compressing the construction times. But more importantly, we have actually been able to push the envelope because we are able to overcome the obstacles that are inherently present in the construction. There's also one more notable thing. As we move to the left, the structural systems have become made of concrete. If you look at the structural systems of these buildings on the right, the structural systems are entirely made of steel. That means the beams, the columns, the main structural elements in the building were assembly of steel elements. But as we start coming to the left, you see concrete starting to play a dominant role, where in Burj Khalifa, you have a concrete structural system in place. So, which means that now there is an inherent advantage that concrete offers, which is becoming the choice material for construction of super talls. Now, just some more statistics. If you look at super tall buildings, and if you look at the 100 tallest buildings in the world, 59 of these are in Asia. 23 are in Middle East, and only 18 of these are in the rest of the world. That means in terms of technology, for once, most of the advancements, at least when it comes to implementation, is happening either in the Middle East or in Asia. There is very little that's happening in the West. That's the exciting news, or the exciting part of this construction. The second thing is concrete is starting to play a more dominant role in the structural systems. And of course, like I mentioned, Burj Khalifa, which is the current tallest building, and the other, the building which is planned in Saudi Arabia, which is 1 kilometer in height, the Jeddah Tower, is also has a concrete structural system. So which means that concrete is now able to deliver the performance that is required. So let me just again harping on this topic of talls and super tall buildings. This is a bar chart that shows going from 1930s to 2018 how the structural systems have progressed. 1930s, if you look at the tall, super tall buildings, essentially all of these buildings went with steel superstructures. Somewhere around here, 2000 is where we had the World Trade Center. Suddenly, the weakness in steel was exposed, and then after that, concrete started playing a more and more dominant role. But if you look at concrete, concrete was already starting to increase its share starting from 1980s. Now, it's come to a point where today, 63% of the buildings which are over 200 meters tall, as they were completed in 2018, these had concrete structural systems. Now, concrete combined with composite construction, these, if you look at the construction today of super talls, these take up the lion's share of construction. Now, that has, and if you look at pure concrete, the share of pure concrete construction is also increasing. The reason that is happening is because we are able to now produce concrete that delivers performance in terms of strength, which is the obvious thing. We need concrete to be strong. If I want to build a super tall, I need concrete to be super strong. Now we are able to produce concretes that are very, very strong. But the story doesn't end there. We are able to now produce concretes that are pumpable. I can now produce concrete mixes, and I have concrete technology that allows me to pump concrete to 800 meters in height. I can literally pump it to that height. Now, that is a great advantage to have when I'm trying to produce a structure that is a super tall. So there has been significant advancement in concrete technology in terms of material mix designs and in terms of pumping technology. Then construction techniques. So now we have better construction techniques which allow us to speed up construction. And of course, affordability. One cannot beat concrete in terms of affordability. And when you compare it across the spectrum with all the other construction materials, concrete is the cheapest. So here I have a material that I can engineer. I can engineer the material to deliver performance, which is cheap. And therefore, it is set to become the material of choice in the future. And of course, it also offers us the advantage of recycling. Now we're talking about recycling concrete and using it as aggregate in concrete. So it is a very recyclable material. So all of these things combined are basically pushing concrete as the choice material for construction. Now, now we talked about performance. So one thing that the people in concrete, people researching in concrete have realized that we need to come up with this performance-based design. Now, just to give an introduction of what performance-based design is, this is a methodology where basically the criteria, these could be structural criteria or material criteria, these are expressed in terms of achieving a performance objective. So I now express the requirements in terms of performance that I expect from the material. I do not specify something that is merely limited to strength. Now, when it comes to concrete material in particular, there are two things that are now being looked at. One is performance during formation. That is, as I'm placing my concrete. This in itself has become a major field where now we are expecting concrete to perform even while I'm placing it. I cannot do form-free construction, digital construction, unless I am able to produce concrete that meets that requirement. And so that has become an important part of performance evaluation of concrete. The other part is performance during service life. I've made my concrete structure, I put it in place. Now I want this to be durable. I want it to be long lasting. So that is the thing that these are the two criteria that now we look at when we're talking about performance of concrete structures. And of course, you contrast this with the conventional method where everything is prescriptive. And somehow we assume, if you follow the current code of practice, that the grade of concrete, the M designation that we have, the grade of concrete somehow provides us all the answers. Grade is just a strength measure of concrete, but somehow we assume that if I have a stronger concrete, it's also durable. And hopefully later in the slides, as I go through my presentation, we'll realize that strength, in fact, does not directly tell us about durability. And we therefore have to look at performance objectives and tailor our concrete, basically by engineering the material, by focusing on the mix design, by focusing on the processing that is required to deliver on the performance criteria that we need from that particular concrete. So performance specifications, like I said, the materials perspective, we have formability. How formable is concrete? Placement and speed, this has become important. And of course, long-term durability. These are the performance specs that we are expecting from the material perspective. The structural performance specs are already in place. I mean, people have worked on performance-based design, in particularly for seismic design. This has been advocated, and it is slowly finding its way into the codes of practice. So this is something that anyway is existing, but from the materials perspective now, a lot of codes are moving into performance specs for material design. Just to show you about performance measures of concrete. Now we are talking about performance measures of fresh concrete. We're talking about things like flow, pumpability, filling ability. These are now becoming essential performance objectives of concrete by which we judge the performance of concrete in the fresh state. Then the performance in the hardened concrete. The performance of the hardened concrete comes, strength as a primary criterion, because as a structural material, it should be strong, but also long-term durability. This is also now getting tagged into the performance measure of concrete. If I'm able to satisfy these two, and then I would have assured performance from the structure. Just to give you one example of performance measure, this is a Union Square building in Seattle, where they've used concrete that is 131 megapascal. So it's a very strong concrete, but the modulus of elasticity of concrete was also specified. So they expected concrete to have a minimum 41 GPa modulus of elasticity that was required for the stiffness. And because if you remember, the sway, the deflection of the building depends not on the strength, but on the modulus. So in this particular case, they specified this as a requirement of the concrete, one of the properties that was specified. So if I now want to start making concrete that I can tailor, here is what is required from concrete. We require concrete to flow like water. That's one of those things that most people desire. It should set on demand. That is, I fill my form, or wherever I place it, it should set after I put it in place. It should gain strength very rapidly, so I can do fast construction. It should be durable to infinity. That's, of course, a dream. Look like new without maintenance. So once I've made a concrete structure, it should look like it can be maintained. It can maintain its own appearance without much investment of money. And of course, everything has to be managed at a low cost. Now, the way we are taught concrete is that it's a basic combinatrix of cement, water, and aggregate. But if I have to hit all of these objectives, then I cannot hit it just by playing around with the basic combinatrix, no matter how hard I try. So the only way I can do this is by bringing in admixtures. So now, today, when we talk about a concrete mix, it is a very complex mixture of course, the basic elements, cement, water, aggregate. In addition, we have a lot of admixtures. We have chemical admixtures, mineral admixtures. We have a lot of fillers that go into it. And it has become a very complicated material where we're able to engineer the material by playing around with the composition, by bringing in additives to deliver on the performance requirement that we are desiring. Now, so when we're talking about high performance, there's now performance requirement during construction, during placement, and performance requirement in service. Let's look at the performance requirement during construction. I would like to engineer the material performance for pumping. If I have to pump concrete, the concrete should be able to withstand the pressure that I pump it to. Then there is this talk of self-leveling or self-consolidating concrete. I want concrete to fill the form. If I'm using form-based construction, fill the form by itself without much effort. So that means it should flow like water. It should be self-leveling. It should level under the force of gravity without having to push it or without having to vibrate it. Then, of course, the final thing is the formless placement, where I can literally go and print a structure. That means the concrete, once it comes out of a nozzle, keeps its shape, and then I can print the entire structure simply without the use of any form work. So just to show you that this fresh performance requirements is becoming important, this is Burj Khalifa, and concrete was pumped to a height of 601 meters. Now, which means that, of course, the technology to pump is available. I have pumps available that can lift concrete to that height. And the material itself was engineered so that once you pressure it to such a high head, of course, the head that would be required would be higher than 600 meters. The concrete should not segregate. It should flow like a homogeneous mixture. That is easier said than done. This requires now understanding what happens to concrete when you pressurize it and how it flows in a pipe. And of course, it's an inhomogeneous suspension. You have aggregate, you have paste. You want to keep everything homogeneous so that once you pressurize it at one end, it comes out of the other end in the same state without showing any separation or segregation. Now, this is another super tall, the World Trade Center, where concrete was pumped to 103 stories in a single pump. Just to show you how performance-based specifications are coming up now. This is one World Trade Center. The specifications placed on concrete was that concrete had to be made with less than 236 kgs of cement per cubic meter of concrete. So this was a requirement placed by the client. In addition, the requirement was that columns up to 40 floors had to be of a concrete of 80 to 95 megapascal strength. The upper floors were 60 to 70 megapascal mix. Of course, these are 56-day strength. And in later part of my presentation, we'll see why 56-day is important. And of course, the performance requirements are here. The concrete had to have a flow, not slump. It is slump flow of 600 to 710 mm. That means it literally spreads itself very easily under its own weight. It should have the ability to pump at least 15 floors for the 95 megapascal mix. And the concrete, which is 80 megapascal mix, had to be pumped to a height of, or should withstand, should be pumpable to 40 floors. And the maximum heat that is produced in the concrete during hydration should not exceed 70 degrees Celsius. Now, if this is the performance requirement that is being put in place, then now the contractor it's his responsibility or her responsibility to deliver concrete that meets all of these requirements that are put in place. And this is a typical performance-based specification that is now emerging as we are using concrete in construction today. Where are we headed with this? We're talking about concrete that meets the requirement of pumping and self-leveling. That means it basically fills the formwork under its own weight. And of course, the final frontier is this digital manufacturing, where I can assemble the whole structure layer by layer and print the entire structure without the use of any formwork. Now this, if I want to implement it, so if I want now to implement this control of performance during placement, then we have to start looking at this term called rheology. We are now starting to understand the flow behavior of rheology of concrete, and the understanding the flow behavior of fluids is this field called rheology. And rheology has been in existence for a long time, except we as civil engineers have never paid attention to it. And now we are being forced to look at it and bring in the concepts of rheology into our concrete mix design. And there is a lot of talk of packing control. So we're talking about how to pack the aggregates. Then there is use of nano additives, which basically specifically enhance performance or rheology of concrete, and admixtures that help concrete flow in a specific way. One of the most commonly used admixtures everybody is familiar with is the water reducer. It basically reduces the demand for water. So here you have concrete that has a slump. If I add a little bit of high range water reducer to it, it basically starts flowing. And this is just to show you what this water reducer does. This is one of the additives we add to concrete. And basically it decreases this property called yield stress. Yield stress is a measure that we get from rheology, rheology measure of cement. And when we add, suppose I take cement paste, which has a very low water to cement ratio, this is how it would fill inside a container. It won't empty out. If I add a few drops of this high range water reducer, I reduce the yield stress and then the cement paste starts to flow. And so this is just a schematic representation of how I can reduce the water demand for concrete with the use of high range water reducer. So basically, I'm able to produce the same flow with much less use of water by the use of this high range water reducer. Now, the high range water reducers themselves are very complex polymers. These are engineered polymers that are specifically done, engineered so that they have this comb-like structure with these teeth sticking out. Each of these polymers sticks to the cement grain. It produces steric hindrances between cement grain particles and basically deflocculates the structure cement grain suspension. It starts flowing very easily. So this is now a field in itself of how to control the flow behavior of cement paste and concrete. And we are basically bringing in material processing of other domains to help us in this job. So how far can I take this? Now, I can, of course, make concrete flow very easily, but I can also have concrete mixes that are very stiff. One example of that is I can have an engineered stiff mix which basically is used in this machine that is used to form pavements. As you see here, concrete pavement is literally extruded from this machine, and after it comes out, it doesn't need form work. It's basically, as the machine is pushing the concrete out, the concrete mix is engineered to be very stiff so that it keeps its shape. So this is one way of speeding up construction, and it's already being used in pavement construction. The other place where we use this very stiff concrete mixes is in the production of these hollow core slabs, which are used extensively in precast construction. This again is possible by using very stiff concrete mixes. So these are literally produced by an extrusion process. You extrude concrete, and after concrete is extruded, it will have the shape, and the concrete is expected to keep these holes, keep the shape without collapsing. And that's only possible if I can produce a material, engineer the material by using these water reducers, microfines, and retarders, which are all admixtures that we use, controlling the rheology of the material to deliver the stiff performance. Now, one step further. So as we were going along, we realized that somewhere down the road, we realized that slump, as we looked at concrete, is not an adequate measure of flow behavior. Just to illustrate that, as we started building and we started using more and more steel to make longer span structures, the congestion in the steel started increasing. And what we understood about concrete at that time was slump. So at some point of time, it was realized that if I produce a high slump concrete, it still does not guarantee filling ability of the concrete. It just merely tells me that the concrete is slumping to a certain amount. So as you can see here, this is a heavily congested steel, and concrete just did not fill all the gaps. So at that point of time, a realization came that we have to now look at this behavior of concrete and start producing concrete that flows easily. And this is different from slump. And just to show you the need for this self-consolidating concrete, SCC as it's called, this SCC basically flows very easily, and it would fill all the gaps and cracks and everything that's available. Now, just another example of a cast in situ pile, and you can see the concrete just did not penetrate. This is high slump concrete, but it got stuck at these openings in the rebar. So at that point of time, self-consolidating concrete was researched, and now we have this concrete that can flow. It levels itself. It basically finds its level just like water. That is only possible through rheology control of concrete. And today we are producing a lot of self-consolidating concrete. The beautiful thing about SCC is that when it's used in structures, it gives you nice mirror finish. So if you see here, these are pre-stressed girders made with SCC, and you get this beautiful finish. So I need not plaster my concrete structures. I can basically have a form finish. It speeds up construction. I don't have to vibrate it, and I don't have to worry about all the lack of compaction that happens in highly congested areas of steel. So just to show you SCC, we did a lot of research on self-consolidating or self-compacting concrete. So much so that we have extensively used it in IIT Hyderabad campus, where we produced most of our structures which are plaster free. Basically, it's exposed concrete. And if the video would work, I can show you what SCC would look like. So you see, this is concrete that is a self-compacting or self-consolidating concrete that, as you could see before, was able to fill the structure under its own weight. It flows under gravity, and it compacts by itself. It is able to fill the structure or all the gaps between the steel without the need for vibration. So this again was possible by engineering the mix to have this property of self-leveling ability. Then now we are coming into the domain of form-free construction, which is taking us into 3D printing. Now we expect mixtures which are 3D printable to have 3 or 4 essential properties. It should be pumpable. I should be able to pump the concrete. It should have a non-segregated flow. As I'm pumping, it should flow like a uniform mixture. it should have shape retention. When it comes out of the nozzle, it should keep the shape of the nozzle, and it should be buildable. I should be able to stack multiple layers and build the entire structure. And that again brings us into rheology control with the use of admixtures. Now we need to understand really the rheology of this concrete, which takes us into the domain of understanding what is known as thixotropy. This is a rheological property that talks about the internal structure within the cement paste, and which we can manipulate to start creating or start stacking up layers as we print them. We need a material mixture that is low viscosity under flow. As I pressurize it, it should flow easily and should have a high yield stress. So that means it should keep its shape once it comes at rest. And this is possible by using, of course, water reducers. We use a lot of nano and micro fines because these help enhance the rheology, and retarders. And now we are also starting to use clays into concrete because they give us that fine rheology control that helps us build a structure layer by layer. Now with this, essentially, I can assemble a whole structure layer by layer. And this is just to demonstrate how a structure would be built. If the video would play, you would see that a 3D printed concrete structure is essentially assembled one layer at a time. And you can see all the multiple layers as they're being stacked up. This is how the layers have been stacked up. And now you can do form-free construction. You're not limited to rectilinear shapes. And the entire structure is assembled layer by layer. But of course, there are challenges here, is that we're still learning how to integrate reinforcement into this concrete. So that is an active area of research, which will basically, once we solve that riddle, then we should be able to 3D print structures of the future. Now, moving on. So we've looked at concrete performance in during placement, but we also have to look at concrete performance in service. What do we mean by saying high performance concrete, particularly from a service point of view? This is concrete that serves the intended purpose and provides an extended service life with minimal maintenance costs. That is what we expect from a high performance concrete when we're looking at service measures, when the concrete structure is in service. If I enhance the durability, then I get a long lasting structure. This is a structure, this is 2000 years old. Of course, it's made of masonry, but it is an aqueduct that is still in use. So this is a classic example of a long lasting structure. And if we could make all our structures such, then we have basically tackled the problem of sustainability. Now, high performance concrete in service, of course, we are making high performance concrete, or at least something that goes under the tag of high performance concrete. It's extensively being used in bridges, tunnels, high top buildings, etc. And this high performance concrete is being developed for particular applications and environments, because now I have to tailor the concrete to last long in the environment in which I place it in. Therefore, that becomes important. So high performance concrete is a concrete that has been designed to be more durable. That is the key thing. And if necessary, stronger than the conventional concrete. So we are removing the link between strength and performance. We're saying strength is may be required, may not be required. It's basically the durability that is important. And HPC concrete mixtures are composed of essentially the same materials as conventional concrete mixtures, but they're proportioned, designed, or engineered to provide the strength and the durability. That's the key thing. This material engineering has now come into our lexicon. It's come into our dictionary. And which is the durability which is needed for the structural and environmental requirements of the project. So what is high strength? Well, now today, at least in concrete, we consider 55 megapascal or greater to be high strength concrete. So now, of course, this is just a random number and it just keeps moving up. So probably for another 10 years down the road, this may be M60 or higher, which would be the dividing line between high strength concrete and the regular concrete. Now, when we're talking about high performance concrete in service, we have to come up with specifications of concrete. That means we need to understand what is the performance requirement it is supposed to meet. The way it is tackled in the codes currently, today, if you look at the code, IS 456 or any other concrete code, there are prescriptive measures in the code. And somehow the codes feel that if you put prescriptions in place, you get durability. The way these prescriptions are put in place is by saying maximum cement content, there's a cap put on that. There's a limit on the water to cement ratio. There is a limit on the supplementary cementitious materials, fly ash and slag. There's a minimum cement content also that is specified. So somehow the codes feel that if these are specified, you're automatically assured durability. But performance measures of hardened concrete would actually, we would have to come up with performance measures and make sure our concrete is measuring up to those performance measures. Strength and stiffness, of course, are primary measures, but then we have to come up with measures of this long-term durability. And of course, we have to, the big challenge here is evaluation of performance of concrete. How do I evaluate performance of concrete? So just to illustrate one point of high performance concrete in construction. Now, most of our construction, we specify 28-day strength. Now, if you look at a high-rise building, typically, the concrete that is placed at the lower floors would not see a very high stress, or would not even see any significant stress till much later. So where is the rush, and where is the requirement to specify this 28-day strength? So instead, if we can specify something like a 91-day compressive strength, so the concrete gains strength little less rapidly, but then I can achieve this using supplementary cementitious materials that overall reduce the heat generation, and they also enhance durability. So there's a requirement to think about it holistically, where we are not just rushing to specify early strength gain where it is not required, like in this particular example. Now, when it comes to performance measures, I have to have tests that are available. So here is a laundry list of tests that are available. Of course, these are all American standards, because we need to figure out what is the performance measure that we require. And the performance measures, of course, we have starting from strength to abrasion resistance, to permeability, penetration, sulfate attack. These are all performance measures that we typically expect from concrete. And then we have a list of tests that we can do to assess the performance of concrete against these performance measures. Now, so the durability that we need to assess, what are the fundamental concerns of durability? The prime concern of durability is corrosion of steel. If I have steel in concrete and the steel starts corroding, the minute steel starts corroding, I start losing my structural capacity. And it is induced by chloride, which gets into concrete, or it is induced by carbonation. Then I have some other material issues, like I can have sulfate attack or alkali aggregate reaction of the aggregate, freezing and thawing when I'm in the part of the country where freezing is an issue, and shrinkage of concrete. And these are all performance requirements of durability. Now, all of them need not be of concern. In some places, only corrosion may be a concern, or combination of these may be a concern. So we will have to basically look at the factors that are of concern and come up with performance measures for those factors that we are concerned about. A typical chart that talks about durability requirement of concrete. This is a concrete beam. This is the core concrete, which is also called heartcrete. The cover concrete is what protects that steel. And it's basically to ensure durability, I have to make sure that this cover concrete is very durable. So that's basically one way of looking at durability of reinforced concrete section. Now, here, the issue is that if I had to protect the steel, then I have to prevent chlorides or carbon dioxide from getting into the concrete. So I have to look at what is known as the transport mechanism into concrete. Now we have to look at how do these elements, whether it's a gas, which is carbon dioxide, or ions, which are chloride ions, how do they get through concrete? So a lot of work is happening on trying to understand how carbon dioxide moves through concrete. How do chloride ions move through concrete? And basically that has led to the establishment of durability test methods. We have test methods that are available that help us quickly evaluate the chloride permeability of concrete. How fast, or what is the penetration resistance of concrete to chloride ions? And there are different tests that have been standardized for chloride penetration. If I was to do this in real life, it would take months. And of course, if I have to develop a concrete mix design and wait for months for the test result to come out, it's not possible. So these accelerated tests have been developed, which give us results in a very accelerated manner, which basically help us assess if the concrete I have produced has adequate resistance to chloride penetration. We have similarly other methods to assess chloride penetration. There's a diffusion test that measures how fast chloride ions can diffuse through concrete. There are gas penetration methods of like oxygen penetration or the air permeability or the accelerated carbonation test, which tell us how fast can any gas like carbon dioxide move through concrete. And there are methods of assessing water permeability, because if water can get in through concrete, then again, steel will start corroding. So there are ways of assessing that for concrete. And these are all accelerated tests that give us results in a matter of minutes or hours. Then there's, of course, the measurement of resistivity. Resistivity tells us how rapidly things can move through concrete. Just to show you how this would work, this is one of the experiments where we're looking at chloride getting through concrete. This is the profile of chloride. Chloride was placed at the top. So here is the depth of concrete. So this is where this is the surface of concrete, and this is we are walking through the depth of the concrete. Chloride was put here, and if you look at control concrete, chloride was able to get through very rapidly through this concrete. But the minute we added some blast furnace slag and fly ash, you can see that now it is finding it tougher and tougher to get through concrete. So we can engineer this material to cut down on the penetration of chloride ions in concrete. Now, we've also now developed these test procedures, these rapid test procedures like rapid chloride penetration test, which basically allow us to assess what is the allow us to specify measures that I can put in place to ensure, let's say specifically for chlorides, I can put measures in place that will ensure that the concrete is durable against chloride penetration. And typically the way we achieve this limitation of chloride penetration is by densifying the microstructure. We basically make the microstructure very dense by adding fillers. And of course, we have accelerated test methods for diffusion, permeability, and resistivity that help us assess if what we have done is correct. How do we then tie this all together? We basically take the results that we get from the accelerated tests and put them into service life models. And there are several service life models that have been developed. These are quite complex because they bring in the mathematical aspects of ion diffusion or carbon dioxide movement through concrete, but they help us predict what would be the life of a structure. So suppose I'm designing a structure which is placed in seawater. Seawater is very rich in chlorides. I can run these models and figure out how long would it take for the chloride ions to penetrate through the cover and reach the steel. Once the chloride ions reach the steel will start corroding. So that will give me a way of assessing what I could expect as the life of the reinforced concrete structure. So this is now coming into our design of concrete structures, where we're designing for a specific service life, where we say, I will design this structure to last for 75 years, or I'll design this structure to last for 200 years. And all of that is done using these service life models, which require the results of the penetration tests or the durability tests that I've done before. Just to give you an example of how this was done. So here is the concrete that is only 35 megapascal. This was basically to be used in a bridge deck. With the use of ground granulated blast furnace slag, very low chloride penetration was achieved. This was a bridge deck which is exposed to de-icing salt. So basically de-icing salt used as calcium chloride. Chlorides would get through the concrete and the deck steel starts corroding. To prevent that, they produced concrete that was very densified, which had a very low RCPT, chloride penetration value. Just the mix design, this was a mix that was optimized for strength and low permeability. And this was achieved by densifying the microstructure, and it was thought that it would give us high durability. But within a year, the bridge decks all cracked. So this is basically a bridge deck, the photo of the bridge deck, and you can see the bridge deck is thoroughly cracked. Now, the reason for this does not have to do with structural configuration, or this is not a structural crack. The cracking was discovered to be basically running in areas. This is a simply supported bridge deck or a simply supported brick, and the cracking happened right in the midspan. So if I can just show you this is the bridge deck. This is simply supported. All the cracking happened in the midspan, and this cracking happened in areas where concrete deck would be in compression. So it didn't make sense. This was not cracking that was coming from structural reasons. The compressive strength that we got from cores was also quite high. The tensile strength was high. The concrete was also of uniform quality. Then it was established that when we took the core through the cracked area, so if you go up here, this is a core that was taken through the crack. So there's core right through the crack. It was found that in this core, if you see, the crack goes around the aggregate. So this is crack that goes around the aggregate. So it was established that this crack was formed very early. This was basically a crack that formed within the first few days after casting. Because when we tested the core from a healthy part of the bridge deck, so this is the core that was taken from a healthy part of the bridge deck. If you test this core, basically all the aggregate was split. That means once the concrete became strong, once it had gained strength, the mortar in the concrete is stronger than the aggregate, because all the aggregate are split in the split tensile test. So this is what led us to believe that this crack was formed at a very early age. And it was established that this crack was formed because of shrinkage. Concrete wanted to shrink, and the shrinkage was prevented, and that's what resulted in this cracking. And we are now seeing more and more of these shrinkage cracks appearing in structures, particularly in where we're using this SCC, self-compacting concrete. And the reason for that has to do with the densification of the microstructure. We densify the microstructure to achieve one objective, but then it works against us when we are trying to control shrinkage. And more shrinkage cracking. This is in a retaining wall. This was even while the wall was being cast, and you can already see water is getting right through. And the steel would start corroding, and you can already see brown stains of steel corrosion on the surface of the retaining wall. Now, to explain shrinkage, if I take a piece of cement paste, even if I seal it, it basically would start shrinking. This is the amount of shrinkage that I would get if I take normal cement paste. But if I now start adding densifiers like silica fume, then I get a lot more shrinkage. How much shrinkage can I get? Suppose I take concrete which has silica fume in it. I would get almost 1600 microstrain, which is equivalent to raising the temperature or lowering the temperature by 120 degrees. So this is the effect that it has of contraction is the same as lowering the temperature by 120 degrees. Now, if the concrete is not allowed to contract because of restraint from other members, it is bound to crack. And these cracks happen within the first few days. Now, this requires now again understanding, going back to the drawing board, trying to understand what causes shrinkage. Shrinkage is produced by the paste. And now going back to the basic engineering, we need to understand packing. So we understand that when I increase the aggregate size, my paste content increases, so the shrinkage would decrease. And the paste content plays a critical role. So if I have, let's say, if I start looking at paste contents, it's not just the water to cement ratio. As I start increasing the paste volume in the concrete, I get into the high shrinkage zone. And these are concrete mixes that have a high tendency to crack. Now, of course, IS 456 has provisions in it to prevent shrinkage. It is addressed. And the way the code addresses it is to say that, look, provide some minimum reinforcement. The minimum reinforcement of 0.15% is prescribed for slabs, 0.2% is prescribed for walls. The issue is that reinforcement comes into play only after the crack is formed. Just to illustrate that, here, if you look at this retaining wall had shrinkage steel in it, but you can see the crack is a through crack. The crack has already gone through and water is able to get through. So the shrinkage reinforcement really does not do much in terms of controlling cracking, or once a crack is formed, it will be a through crack that comes through. So we need to now address this through good construction practices. And of course, we have talked about curing. So one of the ways to deliver high performance concrete is to pay attention to construction practices, where we have to compact our concrete properly, have uniform quality, and pay very good attention to curing. But what if, despite all of this, my concrete cracks? Then we are looking at another set of admixtures that have been developed. One of them is called the shrinkage reducing admixture, which is basically a surfactant. And what it does is that it basically reduces shrinkage. So this is the shrinkage that I measure from concrete, which is densified. But the minute I add a little bit of SRA, which is 1.5% of shrinkage reducing admixture into concrete, you can see the shrinkage decreases tremendously. So we are now able to produce these admixtures that help us control SRA, the shrinkage. There's another set of additives that we're adding into concrete. These are called superabsorbent polymers. Superabsorbent polymers are what go into diapers. These are materials that absorb water, they hold on to water. We mix them into concrete or cement paste, and the superabsorbent polymers absorbs moisture, it swells, and it basically retains water. And when the concrete starts drying, which produces shrinkage, the SAP releases the water into the concrete mix and basically reduces the shrinkage. Just to show you that if I don't have SAP in this densified concrete, I'll get a lot of shrinkage. By adding just 0.4% SAP, I'm able to completely reduce the shrinkage. So you can see that there's no strain in the concrete. So concrete does not shrink. So these are all things that are now happening on the material front that help us address the issue of cracking in concrete, making concrete more durable. So just to conclude, we're talking about performance-based specifications for the material. We expect concrete to deliver in performance. Strength has always been in the picture. We have the standard M designation or the FC prime designation in America that has been in existence forever. But now we're bringing in durability requirements in terms of ion penetration, in terms of gas penetration into the material. And this is specifically important from a corrosion point of view. We're talking about shrinkage control of concrete. We're talking about ASR and sulfate resistance of concrete. These are specific problems that happen when we have specific type of aggregate or when we have specific types of cements. We have developed accelerated tests that help us assess the performance of concrete against these durability measures. And now we're coming up with limits from these performance tests, so that when we develop a concrete mix design, it's not only for strength, but it will be based on trying to match what we have from these accelerated tests. And we come up with mixed designs with the use of these admixtures that will deliver on these performance requirements. And finally, if we've done our job right, this is what we should end up with. This is the Pantheon in Rome, built by the Romans. It is made of concrete. It is 2,000 years old. This is the structure as it looks on the outside. This is the structure as it looks on the inside. It looks like it was built yesterday. And 2,000 years old, and it's still going. So this is the very definition of a sustainable concrete structure. So with that, I would like to conclude and open the floor for questions.
Thank you, sir. Thank you very much. Thank you very much, sir. A valuable, wonderful lecture stating from the challenges in concrete, from especially high-rise structures and high-performance concrete. So maybe, I don't know, the question is, my side, how it is helping us, maybe codes, maybe we are talking about high-rise buildings. Still codes are, we are talking about conventional methods.
Yeah.
Theory to
Actually,
practice.
as we speak, IS 456 is being revised, and
Yes,
the entire material section is going to bring in performance based mix design. So that's happening. So the concrete mix design that will come up in the revised versions of the codes, this is already being built into it, where we will have to identify the performance requirements, develop concrete mix designs to meet those performance requirements.
Yes, sir. One side we are saying that environmental aspects. Maybe are we really required for high-rise buildings for living human life?
Well, that's one of those things. It's about technology, and whether going tall is important or not is a debate for another debate topic. But yes, one thing about going tall is that you have more efficient use of space. Where space is at a premium, you have no choice but to go tall, right? And you can already see the skylines in the cities have steadily increased. We went from 3-story dwellings to now 30-meter buildings, and now you see, at least in Hyderabad and neighborhoods, it's gone taller and taller. The skylines are going up. So that's the way it is, because land is at a premium. We will have to learn how to go tall. So we have to master tall. There's no way around it. That's one thing. Having said that, then what material do you make it with? So conventionally, it was made with steel because you could assemble faster. You could have these factory-made steel elements. You'd bring them, bolt them, and ready to go. But now, because of all these advances that we have in concrete, we're able to deliver the structural performance, which is better using concrete. And that is possible because we're able to engineer the material to deliver the performance.
Thank you, sir. Thank you very much. There's a couple of questions in chat box, sir. I will read out. Maybe you can also see, sir, in chat box.
Let me see. So,
first question: what about shear capacity of concrete when it is placed in layer by layer?
Yeah, this is a very important question. This is a very interesting question. Yes, it is an issue. The interlayer bond is still something we're working on, but this is something that see, the first thing is to develop the technology, where I should be able to develop the technology, build the structure layer by layer. So it is one of the methods of additive manufacturing. It is done in metals. It is done in polymers. We are able to print with polymers. We're able to print with metals using this layer deposition technique. So we are simply adopting that technique. So once we master the technique of being able to produce a shape that we want, then the next thing would be to come to all these engineering aspects. And I'm not saying that people are not looking at it. This is being looked at. The interlayer bond strength is something that people are working on, of how to improve it, how to integrate reinforcement with it. So there's a lot of work that's happening in there, but it is right now, yes, it is a major concern.
Second question, sir.
As per IAStructE table 2, high strength concrete means strength of 55 MPa or starting from 60 and contradicts your, yeah. So yes, so this is the 55 MPa that I have specified is the cylinder strength. So that was from the ACI definition. So that is the cylinder strength that is being put in there. Why are increasing use of concrete in high-rise buildings? It is, I'm sorry, it is a brittle material, requires bigger size compared to steel structures. Yes. So yes, it is well, it is a brittle material, but we use steel with it. So when we're talking concrete, it is not just pure concrete, it is reinforced concrete. That's the first thing. The second thing is when it comes to it being a brittle material, when you talk about reinforced concrete, I can engineer reinforced concrete to be ductile. And now we have RC structures which are quite ductile, and they're being used in high-rise construction. So even in pure steel structures, it is not uncommon to use, or I would say more often than not, the lateral load-resisting elements typically are concrete. So you would use a concrete shear wall and integrate it with the steel elements just to get that lateral stiffness. So this thing that concrete is brittle and you cannot use it for high-rise construction, that's a myth. That's the first thing. We can engineer reinforced concrete structures for ductility. That can be done, is being done. The second thing is that steel, of course, was the material of choice, but 9/11 knocked it off the perch. The reason is steel is very sensitive to fire temperature, whereas concrete gives you the added advantage that it is it is much more durable against temperature, or it's much more durable against fire, much more longer lasting in fire. So that is one of the big advantages that you gain with concrete. Now, the third advantage that you get with concrete is sometimes being heavy is not necessarily bad, particularly when it comes to wind. When I'm talking about earthquake, then the weight of the structure becomes my enemy, because the force that is generated depends upon the weight of the structure. Heavier the structure, more force it attracts. That is for an earthquake. Whereas when I'm talking about wind, the heavier the structure, or the heavier structure would perform better, because here weight comes to my advantage. So when you go high, when you go tall, beyond a certain height, about 45, 50 meters, wind plays a more dominant role than earthquake. And so in those conditions, then the advantage that you have with steel goes away, and concrete perhaps is probably a better material to use when it comes to the performance against these lateral forces that come from wind. So these are all the reasons that concrete is coming into the fore when it's talking about talls. Now, coming to super talls, being able to pump concrete is a huge advantage, because now I can pump and place concrete to whatever height I want, 800 meters. If I had to do the same thing with steel, I would have to literally somehow carry the steel members up. And in some of these construction sites, which super talls, it's not unusual to see helicopters deliver the steel pieces at the very in the very tall or the very top stories. Whereas here I can simply pump the concrete up. And most of the way the structure is built, particularly the shear wall, it's basically built in a manner where the crane literally latches onto the shear wall and it builds as it goes along with the shear wall as the shear wall is being built. So I really don't need any elaborate support systems or anything as I'm casting this concrete. So these are all advantages that come into play when you're building with concrete. And that is the reason why probably it is becoming more prominent in use in these building structures.
Last question, sir.
What about shear capacity of concrete placed layer? That is done, right? So, yeah.
India is working
on green power solutions, which supports the steel and cement industries to make green products. We can see green cement concrete maybe by 2030, 40. Yeah, this is one of those things where if you look at cement production in India today, the cement plants operated in India are probably amongst the most efficient cement plants anywhere in the world. We've come to the point where in terms of production of and making cement, we are operating the cement plants at the highest efficiency possible. They're at the world standards. But coming to this green tag, right? So green tag is now if you look at concrete, and suppose I start making concrete using waste materials like fly ash or slag. If you look at it from a holistic perspective, I've already offset the carbon tag of cement with the use of these materials. So if you do a net evaluation, then these with the use of these materials, it is already getting green. And going down the road now, I didn't show that in my presentation. We are talking about materials which can be added to concrete, which also provide the ability of scrubbing the air. So there's use of titanium dioxide, which basically provides has photocatalytic action and can convert the SOx and NOx into less harmful forms. So these are all things that are being incorporated into cement and concrete to make it basically greener. And down the road, of course, we cannot completely make it carbon free, but if we can reduce it significantly, and probably go towards a more green future, right? And probably we can incorporate more waste. So that also gives us the added advantage of utilizing the waste of another industry, so that we could get some offset credit points from there. Right? Any other questions? Yeah. Can we see cement product manufactured from recycled or waste materials on larger scale? Larger scale, not yet. Smaller scale, yes, it is taking place. There are companies that are making cement using only waste. That is, yes, it is being done. But of course, scaling it up is an issue. And the biggest problem there is a consistent supply of waste materials. So that is the biggest problem there. See, waste materials are not manufactured. So controlling the quality of waste material becomes a problem. So if you try to scale up to a large scale, then you should have a consistent supply of waste material, and that becomes a problem. So that's what I think some people are looking at to see how scalable these things are. But on a small scale, yes, cements are being produced using only waste materials. That is being done.
Okay, thank you, sir. Sir, Pradeep, sir, you want to add anything else?
Yeah. So thank you, Professor Subramaniam Garu. So that was a really wonderful lecture, and I suppose this is the need of the hour when IS 456 is already started its like major overhaul, and materials is one of the significant changes what you would be expecting. So high performance concrete, and as you rightly said, that the skyline is changing, and many small towns and cities, high-rise buildings are coming up, and concrete is a like major or key player. So if you get good models, and we can incorporate those in the analysis also, so that our practicing engineers take this material in a more practical manner. So I think it's really useful for everyone. Yeah, thank you. Thank you once again.
Okay, sir. Sir, Manoj Mittal, sir, would you like to add anything else?
No, after such a fantastic lecture, actually, I don't have much to add. It was very futuristic lecture, and you introduced many new futuristic concepts and technologies, which will be the future of concrete and the future of the structures which will be coming up. So it is really very interesting that new IS 456 will be coming. And since earlier it was 1978, after that it came in 2000 after 22 years, and and so now after 2000 it is coming in 20, maybe it might be coming 22 only. So it's still again after 22 years. So it is taking a lot of time for us to revise the codes, but yes, it is very, very important, and we need the revised code. But much more than the revision of the code, we also need to make the people aware about the provisions of the new code, so that they can start using it. Because you will be surprised to know that I have seen many large organizations. When I say large, means Maharatna companies of Government of India, they are still not aware about the provisions of IS 456 2000. They are still following 78 kind of a thing. So I'm really surprised and also shocked to see what kind of practice we are doing in India. But yes, anyway, this code is needed, and I am quite hopeful that this will incorporate the latest things, and we will be able to use that. Thank you. It's a very nice presentation. Thank you.
Thank you, sir. It's my privilege to take a vote of thanks. I thank you, Subramaniam sir, for a wonderful lecture, for his inciting to open up our researchers, academicians, and practice engineers. What is the latest development in the concrete industry? So on behalf of Department of Civil Engineering and the entire management, I extended my heartfelt gratitude to the speaker for the sharing an immense knowledge and experience with us. I take this honor to thank all the dignitaries, colleagues for their cooperation and support in organizing this event. I'm thankful to all the participants for attending these webinars. Thank you for your patience, participation. Thank you, one and all, and signing off the day. Have a good evening. Thank you, sir. Thank you very much.
Thank you. Thank you.
Thank you. Thank you all. Thank you.
Thank you, everyone. Bye-bye.